spectroscopy. So, who is ready for that? Jetlin, how are you, Pa?
Yes, ma'am.
Okay.
I'm alive.
Have you recovered?
Yes, ma'am.
Okay, Pa. Can you give answers on previous class? What we have discussed?
No, ma'am.
Just say the titles, no? Just say the subtitles, what we have seen in the last class. For absentees only, I'm uploading the videos, recorded videos, okay? So you must go through the videos. Since we have discussed very fast in the last class, I have focused the slides of last class again. We'll revise again and then we'll move on to the next topic. Okay. Okay, Johnson, can you explain? Johnson or Jackson? Any one of you?
Ma'am,
Yeah, Jackson, proceed.
general application is quality control of pharmaceuticals, ma'am.
Okay.
Uh, and the solution for calculating the drug release
Okay.
we can use, ma'am. In vitro bioavailability testing we can use this, ma'am.
Okay.
Um, Determination of uniform and purity, ma'am. For determining the uniformity and purity of
Mm,
the pharmaceutical products, we can use this, ma'am.
mm.
Mm,
Purity of nanoparticles. Mainly, we'll be seeing about uniformity of nanoparticles in it. Okay.
okay,
When
ma'am.
the nano formulations are made, during that time, we'll be seeing about its purity and uniformity through UV analysis. Mm. And then,
For determining drug-drug interaction and drug-food interaction, ma'am.
okay. Okay. Mm.
Mm, then validating of drug substance, ma'am.
Method development and validation. Mm.
Well, yes,
Mm. Okay.
ma'am. Stability, ma'am. Stability indicating method development.
Mm.
Next, we can determine
pKa or drug substances.
yes, ma'am. pKa
Acid
value of drug.
dissociation constant. Acid dissociation constant that you will be performing in the lab also. Okay. So we will come to know how pKa is determined using UV visible spectroscopy. Hmm. What other applications we have seen? Yeah, I have focused the slides also. You can read from that. So remaining applications can be said by Johnson. Thank you, Jackson.
Thank you, ma'am.
Okay, pa. Johnson, can you proceed? Siranjeevi. Siranjeevi, are you there? Stephen.
Yes, ma'am.
Yeah, proceed, no? Say the applications, remaining applications, what he
Yes, ma'am. Clinical applications,
okay,
evaluation of normal and abnormal biochemical constituents in
okay,
body fluids, ma'am.
okay.
Ma'am, others also, ma'am. Pharmacology,
Pharmacology and pharmacognosy.
pharmacology, in vitro pharmacology, activity studies, and selected drug product, ma'am.
Okay,
And determination of bioavailability of a drug product testing in animals.
good. In
And
pharmacognosy,
pharmacognosy, determination of isolated herbal product compounds.
good.
and determination of quantity and purity of an isolated compound,
Mm.
and in vitro pharmacological activities on herbals.
Okay, pa, good. Thank you, Stephen.
Thank you.
And along with this, what are other topics we have discussed? Can anyone say? Monisha, Monisha, can you explain what are remaining topics we have seen in the last class? Yeah, proceed. Make it fast, no? Anybody else? Akarshna?
Beer Lambert's law,
Beer Lambert's law.
derivation, deviation, and limitation.
Yeah, derivation, deviation, and limitations. You have written a test, right? All of you have written test, no? You need to include some more points to score maximum marks for B. Lambert's law derivation. And some people have copied as such from Ravi Shankar book, okay? From the textbook, the derivation was copied. In that book, no, all the steps has not been explained. You could find from the PPT all the steps easily defined so that you can. It's okay, Monisha. I can understand. No problem. I can give explanation in the next class also. So you need to add some examples of limitations and deviations. Derivation as such, you can write what material I have given, the same derivation you write it so that you will get more steps and it will be very clear to how you are combining Beer-Lambert's law, how you are deriving it, how you are combining it. Okay. And then give examples for limitations and deviations. You have given only points, you just add some examples. Okay. You should have understand now. So you can take some chemical substances as example or pharmaceutical drugs as example, and what case it will be giving positive deviation, in what case it will be giving negative deviation, that you have to give examples. And for applications also, you have to, I have given only what are all the areas it is applicable in different departments, right? We have divided according to the department wise so that it will be easily understood what are all the titles are correlating with that department. And you need to include examples for each category. Okay. And nobody has given examples, and I have not informed also in the last class. You have to include examples. If quality control of pharmaceuticals means take one drug, if you are giving the same title in the net, you will be getting many articles. Okay, from that you can take some examples, one or two examples, drugs studied by UV visible spectroscopy, that you can focus as example. Okay, one or two, minimum two drugs, okay, that is analyzed by UV visible spectroscopic method for dissolution studies or for nano formulation studies and method development validation. For each case you just take two examples so that your application part you will be very clear about that. Okay, for each title you need to quote minimum two examples, where also you have lacked to score marks. As such, you have copied from the title what I have given. For each title, just focus any two drugs as example. If you write with examples, we will understand that you have understood that concept very well. That's why. Okay. So you need to include examples for applications and examples for limitations and deviations along with the material given. And UV visible spectroscopy principle, instrumentation, application I have asked, and nobody has drawn the instrumentation itself. You have to draw single beam and double beam instrument schematic representation. Okay, that schematic representation I have given in the previous slide, I think so. The previous PPT. You can find the PPT notes in the classroom itself. You just download. You can find the schematic representation for single beam and double beam instruments. You have to draw the schematic representation of instrumentation from source of light, monochromator, sample cell, detectors, everything you need to draw diagrams and you have to explain. Okay, and many have not given, and few have drawn only single beam instrument, that also not very clear. Okay, diagram is very important for UV visible spectroscopy. Okay, So all must draw diagram when instrumentation term is asked, and whenever instrumentation merely is asked, you need to include principle also, working principle. So along with the principle, instrumentation should be discussed during exams also. That's why in the class also I have explained principle along with instrumentation, then application separately. So this is how you need to write in the exams. Okay. So these are all in UV visible spectroscopy what I would like to share with you, and what are the things you need to write also. So let's revise once again what all we have discussed in the UV visible spectroscopy. We have seen quantitative applications, pharmaceutical and spectrometric titrations in the last class. In quantitative methods, we have seen single component analysis. It is of two types. When reference standard is not available, what is the method? That is a 1% 1 centimeter method. When reference standard is available, we'll be using direct comparison or calibration curve method. Then multi-component analysis, where multi-component analysis will be going with simultaneous estimation. This is all we have seen. And principle behind quantitative analysis is concentration. Starting in the beginning, we'll be analyzing concentration. From concentration, quantity is determined for the drug substance or drug product. Then purity is analyzed, and that purity says about safety and efficacy of the drug product. Then derivation of Beer-Lambert's law we have seen. It is related to absorbed light, intensity of absorbed light, intensity of transmitted light, and intensity of reflected light. Reflected light will be very small and it is negligible amount, so it will be eliminated. So we will take only absorbed light and transmitted light. And we have seen Lambert's law and Beer's law. Lambert's law says about absorption is directly proportional to thickness of the medium. That's what he explains. While writing in the exam, you need to write exact law. Okay, whatever words given in the law definition, the same you need to write. Use the same term and words also while writing in the exam. Just for understanding purpose, I am saying that absorption is directly proportional to thickness of the medium. That is Lambert's law. What is Beer's law is absorption is directly proportional to concentration. A is directly proportional to C. A is absorbance, C is concentration. Where here A is absorbance, T is thickness. T or B also we can say thickness, you can say with T, or path length. We are saying it as path length. Path length also can be said as T or B. So that's why the equation you are deriving, combining both Beer-Lambert's law, you are getting as A equal to ACT, ACT or ACB. That you can say it as ABC, A equal to ABC. A is absorbance and small a is absorptivity. Small a is absorptivity, C is concentration, and T is thickness. So this is how you need to mention the Beer-Lambert's law. And then we have seen deviations, where positive and negative deviations. It is based on concentration of sample. It will be varying. When concentration is keep on increasing, always absorbance will not be increased with the concentration. Only some limit it will be increased or decreased. And that range only called as linear range. That means in linearity only it is obeying with Beer-Lambert's law. So that we need to find out what is positive and negative deviation. Quote some examples for that. And physicochemical and instrumental factors or limitations for Beer-Lambert's law. So what are the physicochemical parameters and what are the instrumental parameters we have seen? And for pharmaceutical applications in various departments, along with general applications. General applications, determination of lambda max and quality control in pharmaceutics, mainly for dissolution studies, nanoparticle studies, and bioavailability testing. It is applicable. In analysis, it will be applicable for method development, validated method development. You will be learning what is method development and validation. In quality assurance part, I will be explaining you. Okay. And what are drug interactions and drug-food interaction studies also are studied by UV visible spectroscopy. Then stability indicating method, in order to fix expiry date, analyze expiry date, we can go with stability indicating method development for each drug substance. And then determination of acid dissociation constant. And in pharmacognosy, isolated herbals are analyzed for its lambda max, and quality control of isolated compounds are done. Even pharmacological activities of that isolated herbals are analyzed by using colorimetric or UV visible analysis. Then in pharmacology, definitely pharmacological activity studies are performed, in vitro studies. Then bioavailability of drug products in animals, various blood samples are taken. We can convert that sample into, means we can modify the sample in order to analyze by, or we need to prepare the sample accordingly to analyze by UV visible spectroscopy. Then it is analyzed. Then clinically, normal and abnormal bioconstituents and body fluids are analyzed. Mainly blood or serum analysis you will be doing with UV visible spectroscopy. Hope you have done in medicinal biochemistry blood analysis, like serum analysis, serum creatinine, blood cholesterol, blood sugar. This all you should have done with colorimetric method. Even urine creatinine also done with colorimetric method, UV visible spectroscopic method. That's what clinical application is given here. Okay. Then spectrometric titration, where titrate, like normal titration, will be using titrate and titrant. Here titrant will be of your known concentration of substance. Titrate is your analyte, unknown concentration, and the product is derived. This reaction completion is monitored by monitoring absorbance, or observing absorbance in the UV visible spectroscopy, and taking in the graph volume of titrant in x-axis and absorbance in y-axis will be getting different shape of curve. From the deflection of the curve you can find endpoint. Okay, so this is how spectrometric titrations are performed. Here you can find some examples also, you can quote it. Okay, 0.1 molar EDTA is taken as titrant, and absorbance in the y-axis is taken. What is the ideal absorbance? I said that is 0.1 to 0.9. So you can observe in y-axis it will not cross 1 only. Okay, to obey Beer-Lambert's law, definitely ideal absorbance must be 0.1 to 0.9. Why I said this range optimum means in that range only all the samples will obey Beer-Lambert's law. If you increase the concentration more, absorbance always will not be 0.1 to 0.9. It will be above 1 and it will not be linear. If at higher concentration, absorbance also will be high, so it will not be linear. So when it is linear means between 0.1 and 0.9. Okay. So this is what spectrometric titrations, what all we have seen. Is there any doubt in this topics in UV visible spectroscopy? If no doubt, then we'll move on to the next topic now. Next chapter now. Is there any doubt, Pa? So no response. Okay, okay, then we'll move on to atomic absorption spectroscopy now. So under spectroscopic technique, the fourth unit of your syllabus, this is atomic absorption. So we are discussing now in spectroscopy, we have divided according to the classification, we have divided that into two categories. One is electronic spectroscopy, another one is structural elucidation spectroscopy. In electronic spectroscopy, it is again divided into two categories. One is absorption, another one is emission. Now we are discussing absorption spectroscopy. In absorption spectroscopy, what category has been completed now? What type of absorption spectroscopy you have learned now? Can anyone answer? What type of absorption spectroscopy you have learned?
UV visible.
Yeah, UV visible. What type of UV visible spectroscopy, which what category it lies? Molecular absorption or atomic absorption? In what category it lies in the spectroscopic technique, UV visible? Whether absorption takes place at atomic level or molecular level? Anybody? Padma Priya? What about UV visible spectroscopy? Whether it is molecular absorption spectroscopy or atomic absorption spectroscopy? Just give answers.
Molecule, man.
Yeah, molecular level absorption. UV visible is molecular level absorption spectroscopy. Now what we are going to see is atomic level absorption spectroscopy. So it is called atomic absorption spectroscopy. So now the second category of spectroscopy we are going to see, that is atomic absorption spectroscopy. Can you see the slides? Hmm? Can you see the slide? Okay, okay. So atomic absorption spectroscopy, it may be called as AAS. It may be called as AAS. AAS means atomic absorption spectroscopy. So absorption of radiation, electromagnetic radiation. What will be electromagnetic radiation for atomic absorption? It is UV visible radiation only. So absorption of UV visible radiation takes place at atomic level. So if any atoms, what type of atoms, then it will analyze. So same UV visible radiation is passed to whole molecule in UV visible analysis, right? UV visible spectroscopy. So what is the difference in atomic absorption spectroscopy? What specific atoms are analyzed? That is what we are going to discuss. So that atom gives spectrum after absorbing electromagnetic radiation. So it is called as atomic absorption spectroscopy. Okay. Absorption takes place at atomic level. It is called as AAS. Next, we'll move on to the contents. According to your syllabus, what are the contents you are going to learn under atomic absorption spectroscopy are introduction, theory, types of electrodes, instrumentation and applications. Introduction and theory, now you are going to see. Types of electrodes, instrumentation and applications we'll see in the forthcoming class. Okay. So these are all the titles you are going to, subtitles you are going to learn under atomic absorption chromatography. First, let's move on to introduction part. What is generally atomic absorption spectroscopy is? AAS is a technique in which free gaseous atoms so atoms in gas form, the two free atoms, not as a molecule form, free gaseous atoms, which will absorb electromagnetic radiation, that is UV visible radiation, at a specific wavelength. This specific wavelength represents lambda max, that is maximum absorbance for that particular atom is called as specific wavelength or lambda max, to produce a corresponding measurable signal. This measurable signal represents the spectrum. Atomic spectrum, what you are getting through this analysis. So after absorbing electromagnetic radiation by gaseous atoms, that is free gaseous atoms, at particular wavelength, that is lambda max, specific wavelength represents, it is specific to that particular atom. So lambda max, that is to produce corresponding measurable signal. Signal represents your spectrum. So the absorption signal is proportional to the concentration of free atoms. According to the number of atoms present in the sample, absorption signal also will be increasing or decreasing. So it will be directly proportional. When concentration increases, absorption also increases. So it is following Beer-Lambert's law. Absorption is directly proportional to concentration. So that is the concept is taken for analysis of free atoms present, that is present in the optical path. Optical path represents radiation. The instrument you should have seen in a UV visible spectroscopy itself. The path of light is what? From source, it is moving on to monochromator, then it is moving on to sample compartment, then to detector, then to the recorder to get spectrum. Likewise, it is the optical path where the radiation is passed through the sample through different parts of instrument. So that is called optical path. When it is present, when free atoms are present in this optical path, it will be absorbing radiation, and that radiation is directly proportional to free atoms present in the sample. So this is the general idea about atomic absorption spectroscopy. And what type of atoms you can analyze means alkali metals. Alkali group 1 and group 2 elements can be analyzed by alkali metals. Mainly alkali metals are analyzed. Sodium, potassium, the group 1 elements, sodium, potassium, lithium, these all can be analyzed by atomic absorption spectroscopy. And who discovered atomic absorption means Alan Walsh. Alan Walsh was the originator and developer of the atomic absorption method of chemical analysis, which revolutionized quantitative analysis in the 1950s and 1960s. Around 1955, it was developed by Alan Walsh. And who was who I have mentioned, Alan Walsh, and who has developed modern atomic absorption spectrophotometer. So this is what appearance of atomic absorption spectrophotometer. You can find the sample. It will be sucked into the atomizer, where it will be atomized. Sample will be of neutral solution only. We'll be discussing now in theory how we are going to prepare sample, how the free gaseous atoms we are getting through for atomic absorption analysis. Actually, atoms, we are not going to take the sample as the separate atom only. We are going to take molecule which is having that heavy metals or alkali metals. Okay, heavy metals or alkali metals, calcium, magnesium, these are all heavy metals, and alkali metals, sodium, potassium, lithium, these are all the metals. If it is associated with the drug molecule, then that atoms present in the alkali metals or heavy metals present in the sample will be analyzed or will be separated from the molecule by atomic absorption spectroscopic technique, and that free atoms are analyzed. When you analyze the concentration of free atoms, that will be directly proportional to the concentration of molecule. Okay, so that's what we are going to analyze in atomic absorption spectroscopy. Now let's move on to the theory. So now you know what is overall atomic absorption and who discovered atomic absorption spectroscopy. Alan Walsh has discovered and started and developed atomic absorption method in between 1950s and 1960s, around 1955. And what is atomic absorption? Free gaseous atoms absorbing electromagnetic radiation to produce the spectrum. And spectrum looks like UV visible spectrum only. The same appearance of spectrum will be same like UV visible spectrum. Only the sample analysis is varying. Where we are analyzing molecular absorption, here we are analyzing atomic absorption. That is the difference. Let's move on to the second part, theory. Now we'll discuss briefly about atomic absorption spectroscopy. So atomic theory began with John Dalton in the 18th century when he proposed the concept of atoms, that all atoms of an element are identical, and that atoms of different elements can combine to form molecules. Okay, atoms, regarding atoms, here in this slide we'll see, so that you can understand how atoms are absorbing electromagnetic radiation. Okay, electromagnetic radiation, that is UV visible radiation, at what level it will be absorbed? Electrons, by means of electrons, valence electrons present in the molecule atom, it will be absorbed. So what are the electrons we have seen? Bonding and non-bonding electrons. Mainly pi and n electrons are responsible to absorb the UV visible radiation. So now we'll see how atoms are absorbing UV visible radiation at its valence electrons. In 1913, Niels Bohr's atom, you should have heard. So Niels Bohr revolutionized atomic theory by proposing quantum numbers. Quanta represents what? Photon. So quantum numbers, positively charged nucleus and electrons orbiting around the nucleus in the what became known as Bohr model of the atom. So nucleus will be of positively charged. Since inside the nucleus, what are the contents of nucleus? Protons and neutrons. So when protons are present, the nucleus will get positive charge. So around the nucleus, in different shells of the atom, you could find electrons orbiting around the nucleus. Electrons of negatively charged. So this is said by Bohr, Niels Bohr in 1913. So that is called as Bohr model of the atom. So atom constitute of nucleus and electrons orbiting around the nucleus. Then soon afterward, Louis de Broglie proposed quantized energy of electrons. quantized energy of electrons, which is an extremely important concept in atomic absorption spectroscopy. So the electrons will be quantized. Means what we can say, these electrons will absorb photons. Photons are said in the term of quantum. Quanta are photons. Already we have seen energy is directly proportional to frequency, that is equal to h nu. H nu is nothing but photon. So electron is absorbing photon. Which electron is absorbing, going to absorb photon, that is UV visible photon. Valence electrons present in the atom. Then Wolfgang Pauli then elaborated on de Broglie's theory by stating that no two electrons can share the same four quantum numbers. So no two electrons definitely share the four quantum numbers, so that it will not, each electron absorbance also will be varying. So that is taken for qualitative study of the atoms. Then these landmark discoveries in atomic theory are necessary in understanding the mechanism of atomic absorption spectroscopy. That's what about atom we have seen now, and what is the role of electrons also we have seen now. Now let's move on to the actual principle theory behind atomic absorption spectroscopy. So atoms have valence electrons. What type of atoms? Heavy metals. Alkaline earth metals, alkali metals, you will be seeing group 1 and group 2 elements from the periodic table could be analyzed by atomic absorption spectroscopy. So the elements are nothing but here atoms. That is said with atoms. So atoms have valence electrons. Valence electron means where it will be present in the atom, in the outermost cell, where valence electron will be located in the atom, in the outermost shell. Why late, pa, Junaid? Junaid, why you are joining very lately? You have not submitted your assignments, class test after your sessionals. Whatever I have assigned, practicals also. Just submit this week. Okay. I don't want to put every time the status in the WhatsApp group. You will be submitting in time. I think so. Okay. All will be submitting in time. So that I have kept only one time. I'll be seeing this week. If anybody is not submitting, again I will be putting your names in the WhatsApp group so that all can see. From principal, everybody can see your submission status. So valence electrons, where it will be presented in the atom, which are the outermost electrons of the atom. You will be knowing that and all, right? Atoms can be excited when irradiated. These atoms can be excited. Excited means going from ground state to excited state. That means the electrons present in the orbital will be in opposite spin. During excitation, it will be becoming unpaired electrons. From paired electrons to it will become unpaired electrons when it is irradiated. So that state is called conversion from ground state to excited state. So which creates an absorption spectrum. So this change. So how much energy is required to excite the atoms to reveal what type of atoms is present in the sample, that is studied by that amount of absorption is studied by absorption spectrum. So when an atom is excited, the valence electrons moves up an energy level. So what um, this term represents means about the valence electrons. They will be, that is from paired state to unpaired state, it will be converted. In the paired condition in orbital, it will be in opposite spin. Spin will not be changed in excited state, but it will become unpaired electrons. So that is called up level, up an energy level. It will be moving with higher energy level. So what energy it has been absorbed to move from paired state to unpaired state? It has been absorbed radiation energy. What radiation energy? UV visible radiation energy. Okay. So what is the electromagnetic radiation used in atomic absorption spectroscopy? What is the electromagnetic radiation used? Anyone can give answers? What is the electromagnetic radiation used in atomic absorption spectroscopy? So nobody is listening, right? If you are answering only, I'll be proceeding. Otherwise, I'll stop the class with this. Saktivel, Rafiq. Yeah, say no.
UV visible radiation.
UV visible radiation, but it is not called as UV visible spectroscopy. It is called as atomic absorption spectroscopy. Why? Since it is specific to atoms. What type of atoms are analyzed? Can you say? What type of atoms are analyzed by atomic absorption? We are not going to analyze all the atoms. It cannot be applicable for all types of atoms. What are the specific atoms are analyzed by atomic absorption? You can only say, pa. Ma. Yeah, Jackson. You also can
Heavy metal.
answers. Heavy metals, mainly group 1 and group 2 elements. Alkali metals and alkaline earth metals. We'll be calling it as alkali metals. Alkali metals are sodium, potassium, lithium and all. Alkaline earth metals are heavy metals. Calcium, magnesium, these are all. Okay. So these are all atoms. When it is associated, you will be seeing many drugs are associated with the metal ions in order to increase its solubility, right? Finite ion sodium, where sodium is attached. Likewise, I could have seen many drugs would have combined with salt form of metals. So that is to increase the solubility. So in order to analyze those drugs, this will be of molecular weight high. We have to go with some other analytical procedures. But one of the analytical procedures to analyze accurately the concentration of metals present in the sample, drug sample, is atomic absorption spectroscopy. Okay, and wherever in whatever sample you find this alkali metals and alkaline earth metals, we can go with atomic absorption spectroscopic method. So the energies of the various stationary states, and thank you, Pa, Jackson and Saktivel, for giving answers. Let's proceed with the
Thank
okay. The energies of the various stationary states or restricted orbits can then be determined by these emission lines. That's what here said as absorbed. How much radiation is absorbed, that is going to be analyzed. The resonance line is then defined as the specific radiation absorbed to reach the excited state. Here, the specific radiation absorbed represents energy of radiation has been absorbed by the atom. So each atom will be requiring different amount of energy. So it will be absorbing the maximum energy. One will be absorbing 500 nanometer, another will be absorbing 600 nanometers, some will be absorbing at 300 nanometers. So it will be varying according to the valence electrons present in the outermost shell. So that will be the characteristic of that particular atom. Sodium will be absorbing at some wavelength, where potassium will be absorbing at a different wavelength. Likewise, each atom will be absorbing at different wavelengths. So how much amount of radiation maximum, that is lambda max, is required, is called as to reach excited state, is called as resonance line. Resonance line, that is energy is matching with the resonance, means some two states will be in equilibrium. What are the two states is in resonance? Means resonance, you note down this term, you will be getting this resonance term in all the spectroscopic methods. When what is resonance means, that is two states in equilibrium. That means energy of atom required to move from ground state to excited state is equal to the radiation energy absorbed. So radiation energy and atomic energy. Atomic means electronic energy of atom. Electronic energy represents what? Energy of valence electrons. So when it is equal to valence electron energy is equal to radiation energy, then only absorption takes place. So that is called resonance line. Resonance means what? Any two states will be in equilibrium. What are the two states here? Atomic energy means I'm saying atom constitute of electronic energy now. So that electronic energy represents what the it is due to the electrons, outermost electrons or valence electrons present in the outermost shell. So that electronic energy, when it is equal to the electronic energy of the electromagnetic radiation, the electric wave present in the electromagnetic radiation will interact with the electronic energy of the atom, so that it is moving from ground state to excited state to give absorption spectrum. So this is called the resonance line. That may be called as lambda max also. If 529 nanometers sodium is absorbing, then that is called resonance line for sodium. Since 529 nanometer is equal to the electronic energy present in sodium atom. So sodium will be having valence electrons. According to the valence electrons of sodium, it will require 529 nanometer energy, means that is the equal amount of energy required for that atom. Okay. So that is called resonance line. Hope you have understood. Next, we'll see the Maxwell-Boltzmann equation gives the number of electrons in any given orbital. So, according to this equation, we can find out how many number of electrons are present in any given orbital. It relates the distribution to the thermal temperature of the system as opposed to electronic temperature, vibrational temperature, and rotational temperature. So, thermal temperature means when the molecule is moving with different energy, it is created. Temperature is created. That is electronic temperature created at electronic level, vibrational level, rotational level. So, these are all the energy levels an atom or molecule will be having. Okay. Then Planck proposed, these are all laws followed for absorption. So you need to add while writing theory. Planck's proposed radiation emitted energy in discrete packets, that is quanta, directly proportional to frequency of radiation. That is what Planck equation, that is E equal to h nu. E is directly proportional to nu. Energy of radiation is directly proportional to frequency of radiation. This is h is equilibrium constant called as Planck's constant. This already we have seen in the first class itself about spectroscopy. You can go through that slide to know about E equal to h nu, and which can be related to Einstein's equation, where energy is equal to mass and velocity, right? M into c squared. C represents here velocity, m represents mass. So when you combine those two equations, we'll be getting V equal to c by lambda. This is the equation we'll get when combining a Planck's equation and Einstein's equation. So that is applicable for atomic absorption spectroscopy, where velocity is equal to concentration divided by c divided by lambda. Lambda is wavelength, c is velocity actually, v is what, c by lambda. That is, c is concentration, v is velocity. Now let's see here, both atomic emission and atomic absorption spectroscopy can be used to analyze samples of atomic same category of atoms, where atomic emission spectroscopy measures the intensity of light emitted by excited atom. That we'll be learning in the next chapter about atomic emission. During learning about emission spectroscopy, you will study about atomic emission. Just here a point added, since that will also similar to atomic absorption, here only emission of radiation is analyzed. Emission of radiation is analyzed. Atomic emission spectroscopy measures the intensity of light emitted by the excited atom. Now what we have seen till now, from the ground state, excited state, the atoms are moving. That is excited state. There it will be always unstable. It has to come to the paired condition, paired state or ground state, normal state. For that, whatever radiation energy it has been absorbed will be emitted. So that is that emitted radiation is of characteristic radiation for that particular atom. So that will be studied in atomic emission spectroscopy. So while atomic absorption measures light absorbed by atoms, where atomic emission represents light emitted by atoms. And this light typically in the visible or ultraviolet region of the electromagnetic spectrum. So that's why it is electromagnetic radiation used as either UV or visible radiation. The percentage is then compared to a calibration curve to determine the amount of material in the sample. So you can compare the standard absorbance with sample absorbance. That's what we have seen in calibration curve method, right? Quantitative method. The same quantitative application can be applicable for atomic absorption also. What are the methods we have seen? Direct comparison and calibration curve method. So both the methods can be applicable here. When reference standard is available, we can go with, for atomic absorption, we will not be having a 1% 1 centimeter method like molecular absorption, UV visible spectroscopy. Here, when reference standard is available, with reference standard only, we'll be performing quantitative analysis for atomic absorption spectroscopy, where we can use direct comparison and calibration curve method. Okay, then the energy of system can be used to find the frequency of radiation. So nu is frequency of radiation, and thus the wavelength through the combination of equations. That is, what are the equations have been combined? Planck's equation, Einstein's equation on the previous slide. And that is nu frequency equal to concentration divided by lambda, where concentration is directly proportional to frequency, and always frequency is indirectly proportional to wavelength. That already we have seen. Because the energy levels are quantized, only certain wavelengths are allowed, and each atom has a unique spectrum. Sorry, here C is not concentration, it is velocity. V here, V, it is not actually V, it is nu. Nu represents frequency. Frequency is directly proportional to velocity. C is velocity, it is not concentration here. C is velocity. Speed of light will be increased when frequency is increased. When more number of waves are passed in through a point in a second, it will be having high speed, right? If only less waves are passing through a point, it will be having less speed. So that velocity is directly proportional to frequency, where it is indirectly proportional to wavelength. That is what this equation states about. So frequency is directly proportional to energy. So when frequency is increasing, energy will be increasing. That's what given in the Planck's constant, where mc square is set by Einstein's equation. So C is velocity. Velocity is set by energy is directly proportional to velocity, who said Einstein said. So that we have, while combining those two equations, frequency is directly proportional to velocity, and it is indirectly proportional to wavelength. When wavelength is increased, frequency will be decreased. That's already we have seen in the first class itself. So again, go through the slides. If you have any doubt, you can go through those slides. The first introduction on spectroscopy, you can go through. So because the energy levels are quantized, only certain wavelengths are allowed, and each atom has a unique spectrum. So this point we need to take, since every atom, no two atoms will be having same spectrum. In the atomic level and present valence electrons present, and atomic nature of each electron will be varying. So that is taken as qualitative parameter for qualitative or characteristics for analyzing each atom present in the sample. So with this, we'll stop the today's class. From next class, we'll be seeing about types of electrodes, instrumentation, and applications and all. Okay, that we'll be seeing in the next class. So we have seen only introduction and theory behind atomic absorption spectroscopy. Who discovered atomic absorption then? Alan Walsh. And what is the absorption? Where the absorption takes place? At atomic level. What type of atoms are absorbing the radiation? Heavy metals. Metals. Generally metals. What type of metals? Alkali metals and alkaline earth metals. Alkaline metals will lie under group 1 elements, where alkaline earth metals are group 2 elements, which are called as heavy metals. So these two category metals are atoms. Can be elements, whatever you can call elements, atoms, metals. Here all terms same only under atomic absorption spectroscopy. Okay, and where it will be absorbing the radiation? At outermost electrons. What are outermost electrons are called as valence electrons. How it will be at outermost state? In the orbitals, it will be in paired condition, that is in ground state, or we can say neutral state also, normal level, from which it is going to excited state after absorbing radiation energy. When the radiation energy will be absorbed by atom? When electronic energy, that valence electron, what whatever energy it requires to move from ground state to excited state, that will be getting equilibrium with radiation energy passed from the optical source, that is from the source of light, UV visible radiation. When it is passed, at what range it is getting equal to the electronic energy of atom, at that case it will be absorbing the radiation. So that state is called, when radiation energy is matching with the electronic energy of the sample, it is called resonance state. Okay, so the resonance lines are getting as a spectrum, absorption spectrum. So it does electrons will be moving from ground state to excited state to give the absorption spectrum of atoms. So this is the main concept behind, the theory behind atomic absorption spectroscopy. We are not going to take the metal, yes, the individual metal. During instrumentation, we'll be discussing the working mechanism, how the source is derived, and what are all the monochromators, what are all the parts, general parts we have discussed in UV visible. Same parts will be there, but specific source and specific monochromators, specific sample cells, this all will be varying. And how we are getting gaseous atom, in what state the sample is analyzed, in gaseous atom, that you have to, gaseous state, that you have to remember, free atoms are analyzed. So in gaseous form, we are converting the molecule into free atom. You will be taking drug molecule in molecular form, that will in solution form, you will be making diluted solution of salt, which is having metals and heavy metals, and that will be converted to gaseous form, that will be splitted from molecule into individual atom first, then it will be converted to gaseous form for analyzing in the atomic absorption spectroscopy. Okay, so that process is called atomization. So everything we'll be discussing under instrumentation part, and what are the applications also will be discussed in the forthcoming classes. So thank you all. If any doubt you have till now, you can arise here and put it in the chat box, or you can ask now. And whatever laws I have said, you just note it down. You can include those laws. Mainly Bohr's model is most important for atomic absorption spectroscopy. Bohr's theory is important. In 1913, Bohr has described that nucleus is having positive charge where electrons surrounding it are negatively charged. That concept you have to be clear about to understand atomic absorption spectroscopy. That's it. So is there any doubt? Okay, thank you all. Thank you all. All of you be safe.
Thank you.
Okay, pa. Take care.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
And I have sorry. Just wait now. All of you join once again, right? Ask them to join. I thought to keep an animation on instrumentation, or shall I keep in the next class? Animation on atomic absorption. It will be posted in the classroom. Already I have posted, I think so. So you can watch that. And I will play now. Just wait. If I ask them to join now, I'll present now. I forgot to present. Yeah, can you observe? So can you observe the video? Johnson, Padma Priya. Rafiq, Junaid. I'll present the video now. They can find the source. This is about instrumentation, atomic absorption spectroscopy instrumentation. How halo cathode lamp, holo cathode lamp. It is not halo. It is holo cathode lamp. Then sample. The radiation light path is formed. Let's see from the beginning once again. So in atomic absorption spectroscopy, what actual process is going to be taken place is shown in this animation process. See, it is source, it is flame, this is sample. Source is called as holo cathode lamp. Atomic absorption spectroscopy source of light is holo cathode lamp. Then sample here is taken. It is delivered to the flame. Here is flame. So in flame, your sample is getting atomized. So where the atoms are formed and the light radiation is passed from the source to the flame. So atoms present, gaseous atoms present in the flame will absorb the radiation. You can see the radiation. And it is striped onto the detector. Detector detects how much amount of radiation has been absorbed by the sample, and it will be given as results. For standard solution, you can prepare different standard solutions: 0 parts per million, 10 parts per million, 20 and 30 parts per million. Where standard 1 is 0 parts per million, that means no sample is there in first solution. So it has to give 0 absorbance only. When light is passed, absorbance will be 0. Next, for sample 2, and for standard 2, so it will be having 10 parts per million of sample solution, which is having atoms. So in the atom flame, it is converted to gaseous atom that will be absorbing. So the intensity of radiation coming from the source will be reduced. So absorbance of 0.1799 will be obtained. Then for the third sample, it contains 20 parts per million, that is increased concentration. The first sample we have taken was 0 parts per million. The second sample was 10 and the third sample was 20 parts per million. Now the absorbance should have been increased. That is 0.3990. So from 0.17 it has been increased to 0.399. Then you have to take standard 4, that is 30 parts per million. So the concentration is serially increased. 10 difference, 10 parts per million difference it has been taken. 10, 20, 30 likewise. Now it is 30 parts per million. So again the absorbance will be increased and the intensity of light passed is decreased. You could observe that is going to detector is decreased intensity since absorption has been taken place by the atoms present in the flame. So calibration curve for copper sample is taken. So for that calibration curve is plotted. Concentration versus absorbance in parts per million. So these are all the readings you should have observed by atomic absorption spectroscopic analysis: 0, 0.17, then 0.39 and 0.58. So you need to plot a linear curve. This for standards. And you have to analyze unknown concentration. Unknown represents your sample of unknown concentration whose parts per million or concentration is not known. So that is to be analyzed. So in the flame, it will be absorbing and the reduced intensity found, and you'll be getting some absorbance for that sample, that is of 0.250. So it lies within the standard concentration. The standard concentration varies from 0.1 to 0.5 and you are getting within that range 0.25 for your sample, and it lies here in the linear curve 0.25 from y-axis absorbance, and you are extrapolating to x-axis, it gives 11 parts per million. So 11 parts per million is your sample concentration. So this is what this is how the sample is analyzed. Hope you understood. Only 5 members are there. You should have seen. Others, through recorded video, you can observe. Okay. Okay, thank you, Pa. Thank you for patient listening. All of you be safe and take care.